Afternoon. My name is Sulayman Muhammad Bello from the Department of Mathematics to give out my lecture on the course called MTH121, that is Elementary Mathematics. Previously, we had a lecture on functions, limit of continuity, and a lot of things have been discussed there. Then my own part, which is the second week, is the concept of differentiation. Then under this concept of differentiations, we are going to look at the derivatives of the rate of change, that is tangent line, first principle, basic rules of the four differentiations, implicit functions, the differentiation of a function, that is chain rule, then differentiation of exponential and logarithm function, and derivative of trigonometry functions. And finally, we are going to look at a derivative of hyperbolic function. Then from the first one, that is derivative of as the rate of change, that is tangent line. Look at the function f of x. A function f of x let f of x be a function defined on a set of x, then the derivative of a function is defined as, that is dy dx f prime of x, the limit of the increment of x tend to 0 of x, comma the increment of x minus f of x divided by the limit at the limit of the increment of x tend to 0 of f of x. Then if you look at this is a tangent line function formula where it gives the formula for a derivative. Then assuming we have this function here, and at x from here, when we replace x here from the tangent line function, that is the formula, as the increment of x tend to 0, when we let our x from the formula here to be a, then we are going to have, here is going to be changed to a, here is going to be changed, where you see a, x, you replace it with x if the limit exists. In what a point limit does not exist, we have discussed that one in the previous function, where maybe you have an undefined limit. Such a limit does not exist. Then a limit exists in many ways, and a limit is differentiable in many ways. Then if you look at this one, when we let our x from the derivative, the first derivative of this to be x, our a to be x, then we are going to have all the way, you see, you replace x there except the increment of x. Then if you look at if the limit of if the limit exists, we say that f of x is differentiable at x equal to a. Then as I said, the limit did not exist where a function is not is undefined, where you have an undefined limit. We have discussed that. Then for example, a function like f of x equal to 1 all over x will not be differentiable as x equal to 0. Then what we are saying there is that if, for example, we let the value of x to be 0, you are going to have 1 divided by 0, and 1 divided by 0 is undefined. Then this one will say that it's not differentiable anywhere. Then we say the limit of a function for which f of x all over x does not exist. The reason why, because we don't have a you cannot take any number divided by 0. That one is not differentiable anywhere. Then for example, let us have another example. Assuming you have a constant value, then in ordinary or a normal derivative, we say that when we differentiate any constant value, you get back to 0. Then let us apply it here in the function of using a tangent line. We say let f of x equal to k, where k is a constant. Then by the definition, what we are saying in the previous one, we have seen that we let our x from the first derivative to be a. Then now when you replace that a with k here from the formula, we are going to have this here. Then if you look at it here, when you take the limit of the increment of x tend to 0 of this one, then you are going to have 0 here, you are going to have 0 here. Then k minus 0, you are going to have k, and k divided by 0, you are going to have 0. That is why we have the 0. Then by implication, when you differentiate any constant, you are going to get back to 0. Why? Because look at the first derivative, and we let our k as a constant to be that our a. After putting that one, then we take the limit of the increment of x tend to 0. What we mean by the increment of x tend to 0, you go through this, or anywhere you see the increment of x here is equivalent to 0. Then now, look at when we take, we have the constant is 0. And the reason why, if you look at it, if you open this bracket, look at, if you open here, you're going to, this is k replacing a, we have this. Then when we take the limit as the increment of x tends to 0, here is going to be 0, here is going to be 0, as I said earlier. Then suppose f of u is equal to u. Then to show by the definition that f prime of u, we are going to get 1. What we are saying is that, assuming you are given a function u and you differentiate u with respect to u, if you look at the power of u here is 1 by direct derivative, the power is 1 and the coefficient of u is 1. And remember that when you are getting the derivative of a function, the power is multiplying the coefficient, then you minus 1 from the power. Then by implication, the power is 1. When you are getting the y, that is f prime of u, you are going to have 1 here multiplying, and 1 minus 1 is 0, and anything raised to the power of 0 is 1. Then to show this one is equal to 1, then using a tangent line, look at it here, f of u, then you come back to this place where you see a here, then we replace it with u as the limit here of the increment of x tend to 0 again here. Then when you open the bracket here, here is u, here is the increment of x, here is minus u, because our f of u is u. Then we replace it here, because here is f of x, and remember we replace it with a, and here we replace it with u. Then when you open a bracket here, look at the bracket, u plus the increment of x here, then look at our u, which is the function given. Then now this u, this one is, when you open the bracket, you are going to have u plus the increment of x minus u, and this u is going with this u. We are going to have only the increment of x dividing the increment of x. We are going to have be left with the increment of x up here and the increment of x down here. Then this divided by this, we are going to get 1. Then if you take the limit of the increment of x tend to 0 of 1, since there is no the increment of x attached to the 1, you are going to have 1. Then going to the next assertion, look at, for any integer, the limit of the increment of x tend to 0 of n is greater than 0. Then by definition, we show that when you are given a function, what we are saying, when you are given a function f of x equal to x raised to power n as it here, then when you are going to differentiate using the higher derivative here, look at it, the power of x here is n, the coefficient of x here is 1, and 1 times n, get n here, and you minus 1 from the power. Then let us, this is by direct derivative. Then if we are to go by using the tangent line, then here, look at it here, we replace our x here, look at it, our x here, then raised to the power, because the power of x here is n with the power of x here, and our function, remember, is given as x, then minus f of x here, because the formula is given f plus x plus the increment of x all over the increment of x minus f of x here. Then our x is from the formula is given with the power of n, we have this minus the function here. Where is the function? The function here, look at it, minus the function here, which is x raised to the power of n. Then using binomial theory, in our Mth121, we know the concept of binomial theory. You know, when the power of the binomial is too large, you know, sometimes, or is fractional, sometimes it's very hard to get the binomial. But when you use binomial theory to handle this case, then we are going to have this one. Look at it. F of x, if you look at it, when you expand this one using a binomial expansion, we have this. We have this one again. We have this one, the expansion. Look at the first expansion, the second one, going to that one. Then if you do the cancellation here, we are going to be left with this one, because this one here is going to be 0 because of the increment of attached to this one. Multiply by 0 here is 0. Then we are going to be left with this one. Then we have proved this one using binomial expansion. Then look at it again. We have shown that. Then what we are saying in this table is we are saying that this is a function, this is the derivative. When you differentiate any constant, one is constant because there is not x attached to it. Then when you differentiate any constant, you get back to 0. Then this is x. When you differentiate x with respect to x, the power of x there is 1. The coefficient of x is 1. 1 times 1 is 1. 1 minus 1, you get back to 0. And anything rest the power of 0 is 1. We get back to 1 here. Then when you differentiate this one, the coefficient of x here is 1. The power of x is 2. 2 times 1, 2. We get this 2. And 2 minus 1, we get this 1x. When you differentiate, going down to the other one, look at the power of x 100, the coefficient of x is 1. 1 times 100 we get 100, and 1 minus 100 we get 99. Then another one, look at another function. We say compute the derivative of f of x equal to 3x plus 1 as the limit of the increment of x tend to 1. And look at it. What we are saying there is that anywhere here you see x, you are going to what we are saying here is that you are going to differentiate this function and the limit of x from the function. Then we have two ways of solving this problem. Either you solve it, you differentiate it using a tangent line first, or you substitute the value of x from the derivative, then before you differentiate. But in this case now, we substituted the value of x. If you look at here, the coefficient of the x here is 3. We have plus 1 here. Then what we are saying here, if you look at it, we substituted 1 here as 1. Look at the 1, the coefficient attached to it. Look at 3. Look at 3. And if you look at it, is 3x raised to power 2. That is how we get this x. That is how we get this 2 after substituting x here. Then plus this one. Then minus. Let me go down to this place. It's well explained here. Minus the function f of x, which is 3x squared plus 1. Look at it here. And the value of x, remember, is 1. We substituted here. Then coming down here, when you open the bracket, 3 times 1, we get 3. 3 times 2, we get 6. Then 3 times the increment of x all square, we have this. 3 times this one, we are not expanding with this one. Then we have this one down, and if you add this one plus this, you get 4. We have this one. Then this 3 minus if you look at it here, you get this plus this, we get 4, and 4 minus 4, we get 0. We are going to be left with this one. The reason why we don't have this one, in the next step is because 3 plus 1 is 4, and 4 minus 4 is 0. Then we are going to be left with this function and this one as the increment of x tend to 0 or both sides. Then now, our next step, what we did there is we factor out the coefficient. We factor out the increment of x outside. Then when we factor out the increment of x is here, the increment of x is factored out, we are going to be left with 6. Then here we are going to be left with 1, the increment of x. So that the increment of x up here is going to go with the increment of x down here. Then we are now going to be left with 6 here. Here, since we factor out 1 here, you are going to be left with 1. Then when we take the limit of the increment of x tend to 0, what we mean by here is that you come to this side, this place, this step, anywhere you see the increment of x, you put 0. Then here there is not the increment of x, we bring this down. The increment of x is substituted here. 3 times 0, we get back to 0. That is our final answer for here. The same application here, another example using a tangent line. Here the f of x is given by 1 all over x, provided that x is not 0. If x is 0, as we said from the previous example, then the function f of x equal to 1 all over x is not differentiable. It's not differentiable because you are going to have unlimited differential distance. Then now we say that if f of x equal to 1 all over x, provided that x is not equal to 0, find f prime, that is dy dx. Then now what we are saying here is that you are going to, the value of x, we are going to use a tangent line, then f prime equal to x plus the increment of x minus f of x, that is the value. Then you come back to your equation. Anywhere you see x is equivalent to x plus the increment of x. That is why here x is equivalent to plus x is equivalent to x plus the increment of x, then minus f of x, and our f of x is given as 1 all over x. That is how we get 1 all over x here. Then when you take the LCM, our LCM is x in open bracket x plus the increment of x. That is the LCM of x plus the increment of x and x. Then now, after taking the LCM, if you take this one here into the LCM, this one will cancel the one in the bracket, remain x, and x times 1, we get back to this x minus, look at minus. Then if you take x to the LCM, it will cancel the x outside here, remain x plus the increment of x, and x plus the increment of x multiplied by 1, we get back to the x plus the increment of x. Then going to the next step, when you open this bracket, here is going to be x minus x, and x minus x is going to be 0, and minus times plus, you get back to minus the increment of x here. Then when you factor out the increment of x here, the increment of x here and the increment of x here, this one is going, then this one will cancel the increment of x down here. Here we are going to have minus 1. Then now if you take out your limit of the increment of x tend to 0 of both sides, then here there is not the increment of x attached to it, we take it down. Here is x squared, there is not the increment of x attached to the x squared, we take it down. Then here there is the increment of x. If you substitute the value of the increment of x as 0, here is going to be x squared plus 0, and we are going to have x squared here left with the minus we got off. Then the next one, find the derivative of this one at unspecified value of x. Evaluate the derivative at x equal to 2, x equal to 3. What we are saying, you're going to use a tangent line to undo this case. Then that is the first step. Then what you got as your answer from the first question, then you are going to evaluate the derivative here again, as the value of x is 2, separate, as the value of x is 3, separate, as the value of x is 4, separate. Then the next concept is first principle. It's the idea of first principle. Then this idea we atomized initially. What we are saying, in any of the 4 or 5 that we atomized previously, you follow, you are going to have the same answer. Then now is the another aspect of a concept of differentiation, which is first principle. Then if you look at it, first principle, initially it has steps. What is that steps? The first step, you are going to be given a function, f of x equal to something. Then the first step, you are going to take the increment in the other side, that is this side, with respect to y, and in the other side with respect to x. Then now, after taking the increment, ideally, you are going to carry y, because here, assuming this is an example, you are using first principle. The first step, as we said, you are going to take the increment in this side with respect to y. Because you have y, you are going to have y plus its increment, that is the increment of y. The other side normally is a function of x, then you take with respect to x, that is x plus the increment of x. Then for a lemma student, after taking the increment, if there is bracket, you need to open the bracket before you carry y to the other side where the function of x is. But you can, at the same time, before you open the bracket, at the same time, you can carry y to the other side. But not to confuse you, expand the bracket first before you carry y. Then when you carry y, that is the second step. Then you do your simplification. After that one, the next step is to divide both sides by the increment of x. the function of y by the increment of x, that is the increment of y divided by the increment of x, and the other side you check with the answer you got, you take the limit of the increment of x again tend to 0. Anywhere you see the increment of x, you put 0. Then the answer you got, that is your final answer. Then let us cite an example. The first example, which is A, we say given y equal to, you know, y is from the definition of the tangent line. Y is the same thing as f of x, which is 6x minus 5 from this first example. Then now, what you are going to do here, in this side, you take the increment y plus its increment. In this side, you take yx plus its increment. Then we say let x be a small increment with respect to x, and the increment of y, the corresponding with respect to, that is the increase in y. You either say increment of x or increase in y. Is the same thing. Then now, if you take this one, this is y with its increment, we have this. If you take here, is x here is attached to 6, you are going to factor out the 6 outside, then you take x plus its increment, we have this, then minus 5 here. Then now, coming down here, we say that we just repeated this one here, but y is equal to x minus 5. Then what we are saying here is that you are going to open this bracket. If you open the bracket, this times 0 you get 6x, this times 0 you get 6 plus the increment of x, then minus 5 here. Then now, after taking we have expanded the bracket here, then the next thing you are going to do is to carry y, this y from here to the other side. Then if you carry y from here to the other side, y is going to be minus y. Then not repeating y, we know that y is given as 6x minus 5. Then you come here, you replace it here, so that you are going to have 6x. Then here is the minus for you know, when you carry y here from here, crossing the sign of inequality, the y will change to minus. We have minus y here, and y is given as 6x minus 5. Then the minus will affect 6 as minus, and minus times minus here is going to be plus here. Then now, if you look at it in this step, 6 here is going with 6 here, because 6x minus 6x is 0. Minus 5 plus 5 is going to be 0. Then what are we going to be left with? We are going to be left with 6, the increment of x. Then, as we said, the next step after your simplification, you are going to divide both sides by the increment of x. Then when you divide both sides by the increment of x here divided by the increment of x here, this one is going. Then now, if you take the limit of the increment of x tend to 0, then since there is no the increment of x attached to 6 after this one divided by this, sorry, there is not this x, is just a mistake. When you take the divide both sides, the x here is going with sorry, this multiply by this, we have this multiply by this, we have this, and we have the minus here. Then this one is going with this one, then there is no this x at all. It's just a mistake. We are going to be left with 6, the increment of x, because the x here is just a mistake. There is no x here. Then the next thing, after dividing both sides by the increment of x, after dividing here is going to be left with 6. Then when you take the limit of the increment of x tend to 0 on both sides, here is going to be the y dx. Then here is going, since there is no the increment of x attached to this 6, you are going to have 6 left now. Then the next one, another example, the same application, when you follow it the same. Then now in this case, y is given as 6x cubed plus 3x minus 2. Then remember we said the first step you take the limit of the increment of, the first step you take the increment with respect to y here with respect to x here. Then here is y plus its increment. Then if you look at this one is 6x cubed. Look at, we factor out the 6, then we take the increment, we have x plus its increment, then raised to the power of 3 here. Then look at this one, there is another function x attached to it. Factor out the 3, we take the increment, x plus its increment minus 2 here. Then our next step now, we open this bracket. You're going to make this bracket into 3 times, you multiply itself. When you open this bracket 3 times, multiplying itself, you are going to have this variable from here to this place. And you are going to, we repeated this one down, look at it down. Remember, we did not carry y yet. Then our next step, we open this bracket with this 6 times this, we get this, 6 times this, we get 18, 6 times 3x the increment of x in bracket, we got this. Then look at it, we open this bracket here. This times this, we get 3x. This times it, we get 3, the increment of x minus 2. Then the next step is to carry y from the other place to the other side. And when you carry y to this place, we are going to have minus y. Then when you have minus y there, look at this one that we expanded the bracket here, look at it here. Then we carry y from the other place, we have this. And remember, y is positive here. Crossing the sign of inequality here changes to minus, we have this. But we know that from the question, y is given as this. Then now you are going to replace y here. Then when you replace y there and you open the bracket all, you are going to have these guys here, because the minus is affecting this one, we have this. The minus times plus, we have this, and minus times minus, you get plus. Then now, after opening the bracket, remember this one is going with this one. 1. Then this one here is going with this one, and the 2 here is going with this one. Then when after the cancel, we say when we cancel out as before, we have this. This is what we are going to be left with. Then the next step, remember, we say you are going to divide both sides of this equation by the increment of x. You divide this one by the increment of x, 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 this one by the. Then when you divide this one by the increment of x, the increment of x up here will cancel the increment of x down here. The increment of x 1 down will cancel 1, we are going to be left with 1. 1 here will cancel 1, we are going to be left with 2. 1 here will cancel the up here will cancel the down one, we are going to be left with 2 as how it is. Then when you substitute the value of the limit of x tend to 0 from this side, here is going to be y dx, here is going to be 18. Remember, we cancel out the increment of x after using the division. Then now the same application here, this is your final answer, because if you go by direct derivative, remember from here, if you differentiate this one, the power is multiplying this one, and the power here is 3. 3 times 6 we get 18. 3 minus 1 we get 2. That is 3 minus 1 we get 2. Sorry, there is power of 2 here. There is mistake here. It's supposed to be power of 2 here. Now there is mistake here. There is look at it. When you divide both sides, only the increment is going to remain 18x squared. The next step is supposed to be 18x squared. Then here we are going to have only the increment of x1 here, because 1 down here cancel the other one. We are going to have 18x plus attached to the 1. The increment of x here is 2. The increment of x left here is going to be 3 after cancellation. Then there is no x square here. There is no, sorry, there is no there is omission of x square here, because when we do the cancellation here, it's supposed to be 18x square plus the one left here, because all other variable apart from the first one and the last variable is going to be 0. Then now what we are saying is, because before I dictated the problem here, what we are saying here is that when we do the direct method, the power here is 3. 3 is multiplying the coefficient of x. 6. 6 times 3 we get 18. When you minus 1 from 3, 3 minus 1 we get 2. You are going to have this square. And the power of x here is 1. 1 times 3 we get 3. And 1 minus 1 is 0. And x raised to power 0 is 1. 1 multiplied by 3 we get back to this 3. This one is constant. Remember from previously, when you differentiate any constant, you get back to 0. Then the next example is y equal to sine x. The same approach. You take the increment with respect to y here, you take the increment with respect to x here. When you take for y, you have y plus its increment, you open a bracket, you sign the right sign here. Then there is an expansion in double angle formula. If you can recall, in Maths 111, we did a double angle formula. Then the expansion of sine A plus B is the same thing as sine x cos x, because here we are dealing with the increment is the same thing as this variable. When expanded well, you're going to have this guy here. Then now, after taking the expansion from the double angle formula, the sine x plus, then you are going to now assume this is your A, this is your B. This is your A, this is your B. Then now, if you assuming you replace this one with what we have here, then from the double angle formula, we are going to have these guys here. Then now, the next step, we carry y to the other place. That is why we have this, then minus the y we carry. And what is y? Y is given as sine x. Look at sine x here. Then the next step, we divide both sides. But before we divide both sides, remember the limit of the increment of x tends to 0 on both sides. If you take it, we divide both sides by the increment of x here. We divide this one by the increment of x, this one by the increment of x, and this one by the increment of x. Then remember from the double angle formula again, when you have sine theta divided by theta is equivalent to 1. Then when you replace it here, then look at it, you are going to use that one here. Then you are going to have 1 here. Recall from the double angle formula, when you have a limit of sine x, the increment of x is equivalent to 1 because of when you have sine theta divided by theta from the double angle formula is equivalent to 1. Then when you replace it here in the value here, we are going to have 1 as it stated here. Then now before that one, if you look at it here, we carry this one here to this place. Here we transfer it to this place. Then when you factor out sine, then you are going to have this guy here. We carry this one, look at the variable here is there. We'll carry minus sine x here to this place. This one will shift it. Then when we factor out sine, because it's common, we are going to have cos, then minus, because here is minus here. Then now, another the previous example then. Then the next one example, again, we are still under concept of differentiation. This one is higher order polynomial. It's a higher order derivative. We say find the derivative of the following polynomial function. Then look at the polynomial function here. The first one is x raised to the power of 16. Then the next one is b, f of t equal to 1 all over t. Then next one is this one. Then if you look at it, it's just simple, it's direct. What is the power of x here is 16. The first example, the power of x is 16, the coefficient of x is 1. And 16 times 1 will get 16. When you minus 1 from the power of x, 16 minus 1 will get 15. That is for the first one. Then now, look at the second example, is f of t equal to 1 all over t. Then now, we can, using an indices, 1 all over t is the same thing as t raised to the power of minus 1. Then now, when you differentiate this one, the coefficient of t is 1, the power of t is minus 1. Then minus 1 times 1, we get minus t. We subtract 1 from the power of minus 1, we are going to have minus 1 minus 1. Then look at it, minus 1 minus 1 there. Then minus 1 minus 1, we are going to have minus 2 up. And remember, when we are multiplying the power of t, which is minus 1, with the coefficient of t, we get minus 1, which is this one. Look at it here. And minus 1 times the whole of this, we are going to have this. Then now, when we change this one to fraction, we are going to have 1 all over minus t raised to the power of 2. That is how we got this one. Then the next one, the next example is the same, another polynomial again. If you look at the power, this is f of u. And if you look at all the variable is carrying u, it means that we're going to differentiate this one with respect to u. Then if you look at it here, the question here, the power of u here is 9. The coefficient of u here is what? Is 12. Then we are taking 9 multiplying 12, we have this. Look at it, 9 multiplied by 12, we have this. 9 here multiplied by the coefficient of u. Then you minus 1 from this. 9 minus 1, you get 8. Minus the power of u here is 7. 7 multiplying 3, we have this, and 7 minus 1, we have 6. The coefficient of x u here is 5. The power of u is 3, and 3 times this, we get this. And when you minus 1 from the power of u, which is 3, 3 minus 1, you get 2. Then the here is constant, and remember when you differentiate any constant, you get back to 0. Then now coming down here, 12 times 9, we get 108. And we have our u raised to power 8 here, then minus 2 times 7, we get 3 times 7, we're supposed to get 21 here, because 3 into 7 places is 21. It's supposed to be 21 here. Then plus here, 3 times 5, we get 15. Then with the power of u here is constant already. That is how we got this guy here. Here is supposed to be 121, not 27, because 3 times 7 plus 7 is 14, and sub 14 plus 7, you are going to have 21. Then 3 times 7 you have is 21, not 27 here slide we made. There is just mistake here. Correct it to be 1. Then the next one, we are going to differentiate this function with respect to x. And the function given here, the power of x is 9. The coefficient of x is 7 from the fourth example. Then the power 9 is multiplying 7, which is this, minus 1 from the power 9 minus 1, we get 8. Then the coefficient, look at it, here is the square root of x. The square root of x, this is 5. You are going to have x raised to power 1 all over 2. Then now 1 all over 2 is multiplying the coefficient of x, the root, which is 5. You are going to have this guy here. Then when you minus 1 from the power of x, which is 1 all over 2 minus 1, we have this. Then now 7 times, now you get back to this. Then remember we have minus, because the power here is supposed to, then minus times minus here is going to be plus. Then this one you take the LCM so that you have single fraction. Then when you do so, you are going to have the other answer to be there. Then the next thing, the next step, this is direct, that is derivative from the polynomial. The first one we did tangent line. The second one we did first principle. Then the next one we are going to have another aspect concept of the differentiation, which is product rule and the quotient rule. What is product? Product, remember, is multiplication rule. Then the next one, quotient rule, that is, is the division rule. Then from the product rule, ideally supposed to be given the function, assuming we have y equal to uv, where u and v are the function of x. Look at it, we say let x, because the function is supposed to be y equal to uv. That is how we get this uv. We say let u of x and v of x be differentiable function at x. Then look at it, the u comma v of the x equal to, then what we are saying, when you have that function is not there, ideally supposed to be marker here, we write it, you are going to have what we are saying, you are going to use the idea of first principle, or either tangent line or first principle. You take the increment here with respect to y, the other one you take with respect to u and v. Then when you take with respect to u and v, you follow all the steps, you are going to have this one as the product rule. But what we are saying, we are using tangent line. We have u. But here we replace it with x. Because we say x, where u and v are the function of x. Then we are going to have u multiplied by x plus increment is, remember, is uv. This one with this, then minus u of x and v of x here. Then when you expanded the bracket correctly here, you are going to have this step, this guy. Then what we just did was to add and subtract. Then when you add and subtract, we are going to have cancellation here. Then we are going to have this guy here and this one here. Then now, if you look at it here, after opening, look at it here, we have u of x and v of x, which is this one here, and this one v of x here, u of x. Look at v of x, sorry, u of x here, then plus, sorry, is attached with u of, which is this one, because here we are going to, if you take the limit here is going to be 0 completely. Then we are going to be x plus 0, we have x, then we have u of x here. After taking, then we have v of x here, v of x plus the increment of x, we have this. Then the same approach here, if you put 0 here, we are going to have v of x here, which is this. This is u of x. This is v of x. I think there is some just chop up here. Then what we are saying is that when you follow the tangent line here, this is u of x, then v of x. This is v of x, u of x, after taking it here correctly. Then the next one, if you take the limit correctly, I think this one is correct here. If you take the limit correctly and you put the limit of the increment of x as usual 10 to 0, you are going to have this, you are going to have this. Then here is here is v du dx. Here is u dv dx. Here supposed to be v prime, that is du dx, then v of x. Here is dv dx. That is what we are saying. Look at it here. As how I said, this is du dx. Look at du dx. Then this is v, and look at v dv dx. We have what we are saying. We have proved that. Then there is another way that we can prove into this one, apart from this one, using the first principle to do that. Then if you use that one, you are going to have the same way. Then remember how you are going to do that is the same approach. But in this case, using first principle, remember the function is going to be given y equal to uv. The other side will take with respect to y. The other side with respect to u and v. But it's going to be in bracket. Then you open the bracket. After opening the bracket, you're going to have some function where you can carry your y from the other side. When you carry y from the other side, the next step you divide both sides by the increment of x. Because initially we say that where u and v are the function of x. After taking that one, you take the limit. You cancel the one that you are going to cancel. You are going to arrive at this one. That is this is the formula for the function. The product too. Then let us have another example using this formula. We say find the derivative of, look at it. If I given there is this formula supposed to be u equal to uv. Then if you compare y equal to uv, this is your u, this is your v based on the explanation. Then you are going to let the first bracket to be your u, the second bracket to be your v. Then now from the formula, remember, we have v du dx, u dv dx. You are going to get u from the formula. You are going to get v from the formula. You are going to get dv dx. What we are looking for from this formula is four things: v du dx, u dv dx. Then how are you going to get du dx? From where you let your u to be then you are going to differentiate that u with respect to x to get du dx. V, you differentiate with respect to u to get dv dx. Then now, look at the question here. This is our u. We have gotten our u, we have gotten our v. That is why if you look at it, y equal to this, then we say let u equal to the first bracket, v equal to the second bracket. Then when you differentiate the first bracket to get your du dx, then if you look at it by the other one, the power here is multiplying the coefficient. We get 2 times 3, we get 6. This is constant is 0. That is our du dx. For dv dx, you differentiate this one with respect to x. The power here is 3, the coefficient here is 1. And 3 times 1, we get 3. 3 minus 1, you get 2. That is how we get this one. Then if you take your u, you take your v, you take your du dx, you take your dv dx into this formula here. This is our v, and look, I will replace it with v, and our v is there already. Then look at our du dx. Our du dx is gotten as 6x. We'll replace it from the formula here. Then the next thing is u. And what is our u? Our u is 3x squared minus 5. We'll replace it here. Then the next thing is dv dx. And our dv dx is 3x squared. We'll replace it. Then you open the bracket. When we open the bracket, we have the other guy here. Then the next one is quotient rule. The quotient rule is the same thing. Quotient is division. You're going to have y all over uv. Then the same approach, you either use first principle or we use the tangent line. But remember, provided that if it is division, v of x should not be 0. If it is 0, it's not differentiable, as how we stated it. Then when you when you use either a tangent line or we use first principle, this is what we are going to have. And if you look at it, there is a little bit different with the other one from product here. The formula here is v du dx minus, look at it, v du dx minus u dv dx all over v squared. This is equally and proof in the product, and the student should try this one as how we expanded this one. Then look at the equation, find the derivative of the following function using a product. The reason why, if you look at the previous one, it's just a bracket, it's just a multiplication. That is why we call it a product. But this one is division. Then look at it. The first example, let y equal to this. Then you are going to let the first one be based on this u and v. If you compare it to this one, our u is x raised to power 7 and our v is x raised to power 8. Then this is our u, this is our v. Then you differentiate this one from the formula is this one too. we are looking for 5 things, or 4, let me say precisely 5, because of we are looking for this the square of v. Then now you are going to get your v, you are going to get your u. From v, you differentiate it with respect to x to get the v dx. From u, you differentiate it with respect to u to get the u dx. Then look at our u is identified from the up. If you compare it with this here, this is our v. Then when you differentiate u with respect to x, the power here is 7, the coefficient is 1. 1 times 7 is 7. Then we minus 1, we have 6. Then v, the coefficient of x is 1, the power of x is 6. 6 times, sorry, the power of x is 8. 8 times 1 will get 8, and 8 minus 1 will get 7. Then if you take all these variables with the derivative to the formula, you are going to have this. And remember our v from the formula here, our v after letting our v is x raised to power 3. Then you replace it here, x raised to power 3, and with the power here. And if you open the bracket by law of indices, the power here is multiplying power, and 2 times 8 we get 16. Then after expanding this one with this, we are going to have this guy here, because here is the x. You differentiate u. You differentiate u with respect to x, you have this. You differentiate v here with respect to x, you have this. When you expanded the bracket, you have this. Then the next example again, this is our u up. The next example we say let y equal to x squared plus 5x plus 7 all over x plus 6. Our u is up, our v is this. Then you are going to differentiate this one with respect to x, this one with respect to x again, to get the u dx here, to get the v dx here. Then if you did so, which is like this, look at our u, look at our u, look at our v here, look at our here, look at here, the minus here. Sorry, here is our v of x. Here is our u of x from the definition here. Then when you differentiate, you get back to this function. This one you get back to this function. Then this is our, when you differentiate this one, you know you get 1. When you differentiate this one, you get 2x. 2x plus, when you differentiate this one, you get 5. This one is constant. You are going to have 2x plus 5, which is 2x plus 5, which is this. And remember, this is our v, is multiplying it from the formula. Then if you, this is our u, look at our u here. Then when you differentiate this guy, you only get 1, which is this one. Then if you open the bracket, remember this is our v, this is our du dx. This is, remember this is our u, and remember this is our dv dx. If you multiply this one to get back to this variable, and remember this one minus this one, 2x squared, we have 2x squared is 2 here, x squared is 1 here, and 2 minus 1 you get 1 x squared here. Then we don't write a 1x squared. It's the same thing as 1 here. Then if you look at this one, this plus this minus this, but this one is going with this. This plus this, you are going to have 12, and minus this. Let me see this bracket. X times 2x, you are going to have 2x squared. X times 5, you are going to have 5x. 6 times 2x, you have 12x. And 6 times 5, you get 30. Then the whole of this multiply, and the minus and the 1 multiply by this. We are going to have this x 1 times x squared times this, we get this. We get back to this. Then now when you collect like terms here, this one and this one, you collect it together and you subtract each other, you are going to have this. So this one, 5 times this, you are going to have 17. And 17 minus 5, you are going to have 12x, not 10x. Correct it, not 10x. Then this one is 30 minus 7, you are going to have 21. Then all over, this is our v. Remember, we square it from the formula here. Then we have this. Then if you try this one again, the same approach, you are going to have this. Remember, this is our v, this is our u. Then look at it here. When you compare it to the previous formula, we have let it here. Then if you look at it, the formula here again, this is our v, and our v is the down here. Look at it here from the formula, we replace it. Then the u dx, Then look at the u dx, look at our u up here, we replace it here, minus from the formula, and look at our u, we replace it here, then dv dx, look at it up here, dv, look at it. Then now coming down here, we differentiate this one with respect to x, we get 3. The other one is constant. We differentiate this one with respect to x, we get 5, not 5x, we get 5, not 5x, we get 5. There is not this 5 here. There is also this x here. It's just a mistake. When you differentiate 5x with respect to x, you are going to have 5. Then coming down here, remember this is our u. Remember this is our v. This is our u multiplying the v, here multiplying the u, here multiplying the v. Then if you open the bracket here, 3 times 5 we get 15, and 3 times 1 we get 3. If you open this one with 5, look at it, that is why we say there is not this 5. If had it been, we are going for this, and it is not like that, there is no the x here supposed to be 15x squared. It's just a mistake. This is only 5. Remember, please take note. 5 times 3x you get 15x, and 5 times minus 2 you get minus 10. This is just a mistake again. Then we open the bracket with this minus, we have this. Remember, look at it again, it's another problem. That's why we say it's just a problem. Then now, if you open the bracket again after multiplication with this multiply by this, we get this. Minus times minus, we get plus. Then we have this. Then when you collect like times this minus this, when you collect like times, this one is going to be 0. And 3 plus this, you get 13. That is how we get the other guy. Then the next one is implicit differentiation. The other one we had is just explicit. What is explicit? How do we differentiate explicit with implicit? Explicit, the one we had, if you look at it, it's just one variable, which is x. We differentiate with respect to only one variable. Then this one, if you look at y itself, is going to be differentiated. It's not only a function of x, it's also a function of y. Do you understand? Yes, look at it. We say consider the following two functions. Y equal to x squared plus 2, and another function y equal to x raised to power 4 plus y equal to plus y raised to power 4 equal to 16. The first one here, we are trying to differentiate between explicit and implicit. If you look at this one, it's only a function of x, only one variable. Then we call it explicit. This one with the function of x itself and y itself, two variables again, we say is implicit. Then look at what we are saying. The first equation is called explicit. Can you see it? Function, explicit function degree of y as a function is explicitly. Since the equation gives an explicit expression that is f of x, where in the second one, the equation we can solve for y and at least two functions can be found, y and x. Look at it. Both the functions are defined x implicitly. The differentiation of this class of function requires special techniques. Then let us have another example of this implicit differentiation. Then look at it. Let us find the differentiation of this implicit differentiation. X raised to power 4, y raised to power 4 equal to 0. Then now what we are saying, this is constant. We are going to differentiate both sides. Then we put the function in the bracket with respect to x. Look at it, this one. Then now, what we are saying, you are going to treat y as how you are differentiating with respect to x. You are going to treat y. Then now, look at it. If you differentiate this one here with respect to x, you are going to have this guy, because the coefficient of x is 1. The power of x is 4. 4 times 1 is 4. 4 minus 1 is 3. We have this. Then now, the one y you are going to treat as how you are differentiating with respect to x, sorry. Then look at it. The function here with respect to y, if you differentiate it, this multiplied by the coefficient of y is 1. 1 times 4, you get 4. 4 minus 1, you get 1. That is how we get this one. Then to differentiate the one with respect to x and with respect to y, then we put the y dx here. Then now, after doing that, the next thing is to carry the one you differentiated with respect to x to the other side here. You cross it here. Then when you cross it, it will change from 4x cubed to minus 4x. The one with respect to y, leave it in this side. Then now when you multiply this one through, when you multiply or when you divide both sides, since we are looking for the y dx here, you divide both sides by the coefficient of the y dx, which is 4y cubed. Then you are going to divide this one by 4y cubed, this one by 4y cubed. That is how we get this guy here. Then now if you look at 4 and 4 is common, 4 here is going 4 here, then we are going to have this. Then this, we are going to have x raised to power 3 with the minus y raised to power 3 here. This process of differentiating both sides of an equation with respect to x and y determine the value of the y dx is referred to as implicit differentiation. That's how it's stated. Another one, another implicit again. Sorry, the next one is differentiation. We are done with implicit, and I hope there is no problem with that implicit. Remember, we said that implicit differentiation, this is a situation whereby even y itself is going to be differentiated, but you are going to assume that you are differentiating y with respect to x in that aspect. Then now the next aspect, we see differentiation of function of function. Then another name of this function of function is chain rule. Chain rule. Then chain rule is given by the formula dy is equal to dy du multiplied by du dx. dy du multiplied by du dx. The reason why we say function of function. Now, if this one is dy du, this is du dx. This one will cancel this one. Up here, we're going to have dy here, we're going to have dx. Then now, this is function of function, and look at the formula is given. But now, look at one example here given using a function that is stated here. Chain rule states that if y is some function of v, where v is some function of x, we are going to have this. We have stated it now. Let's look at this formula. Then we let our function here to be our u. Then look at it. Then what we are saying in general here, we let u equal to this and v equal to what is inside the root here. Then if our u, we let it to be what is here, and our v is what is inside the root, then we are going to have this here. Y is going to be changed to u raised to power 4. Then what we are saying here in this case is that when we let our u to be this, then y is going to be changed. This is y equal to this. Then when we let our u to be what is in the bracket here, then our y is going to be changed to u raised to power 4 because we have this. Then now, look at it, we can rewrite it as this here. Then what we are saying in general, in a simpler way, you are going to let this one to be your u. If you let this one to be your u, your y is going to be changed to u raised to power 4. Then you differentiate y with respect to u to get you du dx. Then when you differentiate y with respect to u, you are going to have this. Because the coefficient of u here is this. The power of x here is 4. 4 times 1 is 4. There is just a mistake here. 4 times 1 is 4, not 3. Then 4 minus 1, you are going to have 3 here. Here is supposed to be 4, not 3. Then now, you are going to now differentiate this one here with respect to v. You are going to differentiate. Remember we said that this is our u. If you let this one to be your u, then in general you are going to, if you let this one to be your u, then you are going to have this here. Then you are now going to differentiate this one here with respect to u to get you du dx. Then now if you look at it now is v, because we let what is inside the root to be our v. Then now what we are saying here, if you change this one, the root here is the same to this. Then when you differentiate to get your du, supposed to be the u dx, but let us take it as here, the du dx here. Du dx here, you are going to have 1 multiplying, half is multiplying the coefficient of x, which is 1, and half times 1 will get half. When you minus 1 from the power, you get back to this. Then if you change this one from the law of indices, you are going to have 1 all over, because minus half here is the same to 1 all over, then the root of this. Then you can take this one into the root here. We have this there. You can take this one into the root, because we are going to have 1 all over v 1 all over. We have half here already. 1 half multiplied by 1 all over v raised to power 1 over 2. 1 over 2 is the same thing as this. Then when you simplify back to this and you simplify, you're going to have our du dx as this. dv dx, sorry. When you simplify our dv dx, you are going to, sorry, du dx, you are going to have this. Then if you take it to the general formula here, here it's supposed to be 4, not 3. Because when you differentiate this one here, you are going to have 4, not 3. Then here is supposed to be 4 here. Remember, which is our dy du, and our du dx is this. Then this one, you take it, if you take it, you substitute it back here, you are going to hand. That is what we have corrected it here. Then now if you use your formula, this from here to this place is our dy du. From multiplying by du dx, look at it here from the formula, but here we said dy du, du dx, and dv dx already. We let it to be that another way again. Then now, looking at this, this is our dy du, this is our du dv, this is our dv dx here. Then now, if you multiply each other here, we are going to have this. Then now, coming down here, remember we say here is 4, it's just a mistake here. Look at the 4 here. Then what is our u? Our u, we let it to be this. Then you replace it here. And remember here with the power of 3, you take the power of 3 here. Then when you simplify here completely, here you simplify it together, here you are going to have this. But remember we have v. And what is our v? Our v is 3x here, 3x cubed plus 6x squared plus 2. When you replace it here, you are going to have this. And we have this. Then look at it, we have 1 all over. Remember from here, 1 all over this. Then if you take the whole of this, which is the v dx multiplying 1 here, you are going to have this here. The process of substitution of a variable and differentiating each equation with respect to each variable refers to as differentiation with function of function here. Then the next one is derivative from exponential function. We are going to rush to this one here. Then look at, we say differentiation of exponential and logarithm function. As a way of introduction, we are starting by finding the derivative of f of t equal to the exponential a raised to power t, where a is less than 1, using by the definition of limit, that is limit of continuity. Then if you use that one, look at our f of t is this. Then when you substitute t as the value of that one here, we are going to have this guy here. Since f of t, look at it, what I'm saying, the value of t as this, we have this minus, because what we are going to have, minus f of t, and our f of t is minus a, f of t is a raised to power t minus this. Then when you simplify together here, you are going to have this. From this result, we cannot compute the limit of this now, so that the t, this one here, is a constant variable, provided that the limit exists from this result. We cannot compute the limit this now. Then now we can say that, we can now say that thus the limit this exists for all values of any value of a greater than 1. We can check this using numerical approaches. Suppose a equal to 4. We now want to examine the existence of this limit. Then look at it. We just replace it here. Then what we are saying, the limit of of exponential function, what we are saying, in general, apart from this approach, we're using another limit. We're using a chain rule in some aspects to handle a case of limits of exponential function. And we have seen a chain rule formula where you are going to begin. Apart from, we are going to see some example that we are going to have other than this one. Then you follow, either you follow this one or you follow the other one. But for the benefit of this course, let us restrict it on this one. In some textbooks, you are going to have another idea where if you solve it, you are going to arrive at the same answer. Then the next one is logarithm, limit of logarithm function, log. Then look at it. Let y equal to log of x equal to, we can rewrite this one as ln x. Then when we follow, when you follow the method of first principle here, we take the increment with respect to y. We take here with respect to x, then we have this. Look at y plus its increment, ln x, you take with respect to x, then by subtraction, you are going to have this if you follow first principle. Look at it. What is by subtraction here? You are going to carry y from here to this place. And what is y? Our y is ln x. Then you replace it here. Then look at it. When you follow another, then if you look at it here, y ln x here, you take the increment, and this is the y. We carry crossing the sign of inequality, changes to minus y, and y is given as ln x. Then when you expand it and you simplify, you are going to have this guy here, and the simplification of this one resulted to this place here. Then when you factor out everything here, then when you differentiate log e of x, you are going to have 1 all over x. Then the same approach, what we are saying, if you go to integration, if you integrate this one back, you get, if you integrate this one, you get back to this. If you differentiate this one, you get back to this. That is what we are saying here. Then now, another example here, find the derivative of a function y equal to log e of k. The first one, log e of x raised to power 3, and the second one equal to, the third one equal to y equal to xt. Then now, if you follow the same approach as how we illustrated in the previous example, then look at it. If you follow the logarithm law, log e of k, maybe if you let this one to be equal to y, you're going to have k equal to log exponential y raised to the power of y here. Because if you follow the law of logarithms, the law of logarithms, I think this is from the law of logarithm here. If you have this, you let this one to be equal to y. Any variable, any alphabet you can use, but this one we make use of y here. If you let this one to be equal to y here, you are going to have this. Then when you differentiate this function here, you are going to have this. What we are saying, when you differentiate any logarithm function, when you differentiate any exponential function, you get back to exponential. Then by the definition here, we differentiate this log e here to get the k dy. Because look at it, you differentiate, this is k, you are going to differentiate k with respect to y to get the k dy. Then when you differentiate the k dy here, we are going to have this. Then now, the next thing, we differentiate this one again with respect to y to get, look at it here. This is the k dy, we have this. Then dy dk, you are going to have 1 all over what you get in dk dy. That is how we get this one. Look at here, the k. We let this one to be our k. We differentiate to get the k dy. We have exponential y. Then now, to get the y dk, we are going to have 1 all over what we got in the k dy sheet. That is the y dk. Look at it here. That is how we go to this one. Then when you replace it there, what is our k? Already we let our k to be exponential y. Then here we replace it 1 all over. What is our k? Our k is what? Exponential. We replace it here. Then what we are saying, when you differentiate back this one, you get back to exponential. And when you differentiate log e of k, you get back to 1 all over exponential. 1 all over k here. That is what we are saying here. Then the next one here, is log e of x. Then we say let u to be x raised to power 3. Then we let our u to be x raised to power 3. Then our y here is going to be changed to log e of u. Then now, when you differentiate this one, the y, the x here is going to be, this is our y per se. Then when you differentiate this one with respect to x, here you are going to have the coefficient here is good. This one is going to be 3. The coefficient of x is 1. 1 multiplied by 3, you get 3. When you minus 1 from the power of x, we get back to this. Then y equal to log u, because we let this place to be log u. Then du dx. Then now du dx is going to dy du now. Dy, remember du dx, we get something here. Then dy du, we are going to have 1 all over u. But we know that our u is x raised to power 3. Then we are now going to have 1 all over u raised to power 3. In general, what we are saying, we are still using a chain rule to handle this case. Du dx, remember, we get what? This is our u. You differentiate it. With respect to u, we get back to this. That is du dx. Remember, this is du dx. Dy du, sorry. Then now, du dx, look at it. Du dx, where is our u? We get back to du dx, we get this. And dy du, you are going to have this here. Then now, remember, dy du, we have 1 all over u multiplying du dx. And look at our du dx. Then now, this one multiplied by 1 all over u. And our u, remember, is x raised to power 3. Then you replace it here. Then you multiply this one. We are going to have the order function. Then the next one is derivative from trigonometry function. Trigonometry function, from the idea of limit, still we are using the limit. We have that. Look at the limit of the increment of x tend to 0 of sine a all over a equal to 1, because this one is going with when you take the limit of the increment of x tend to 0 of sine a, you get back to 1 as how we stated it there. Then now what we are saying, if you look at this example here, if you follow the one we previously had using a limit tangent line, you replace sine here as here. If you open the brackets here, this is the value of x plus the increment of x. And remember, after taking that is minus f of x, and our f of x here is sine x. Then remember, from the double angle formula here, when you make your expansion from the double angle formula here, you expand this guy here, you are going to have this, then minus this. Then the next thing now, as how we did from the previous example, we take this one, we take this variable here, divide by this. We take this variable here, we take this, we collect like terms first. This one collecting here, here going to this place again. We take this one to this place, here to this place. After taking this one here, then look at it here. Look at this guy here, look at this guy here. We take this one here, we have this. Because here is positive, here is negative. Then now, we take this one divided by the limit. We take this one divided by, we take this one divided by the limit. Then we have, then now, here, if you factor out, if you look at it, sine x is common. When you factor out sine x here, we are going to have this, then plus this guy here. Look at it. Then if you take the limit of the increment of x tend to 0 of this, look at it. Here you are going to be left with only 0 here. 0. At all here you are going to get 0, because if you put 0 here is going to be 0. Here is going to be 0. This divided by this is 0. Then that is how we get 0 plus here. Then now what we did here, we take, if you look at it, what we did here, look at the equal cos here. If you take it, multiply this one, get back to this. Then look at sine here. Then now, if you take the limit of this one here, as how we stated it here, if you compare this one with this one here, is going to be 1. Here is going to be 1. here, because if in double angle formula, as we stated it previously, you are going to have sine theta divided by theta, and sine theta divided by theta, remember we say is 1, then you replace it with 1. Already completely here is going to be 0 after taking the limit. Here is going to be 0. Then we are now going to have cos x multiplied by 1. Completely here is going to be 1. The 1 multiplied by this is cos x. Then what we are saying, when you differentiate sine, you get back to cos, according to this derivative, if we understand it carefully. Let me remind you, or let me repeat it for better understanding. Then what we are saying, the function given f of x is sine x. Then if you compare with the tangent line, remember, you take the increment. Anywhere you see x, you put x plus the increment of x, as the limit of the increment of f from the tangent line equal to as the limit of the increment of x is 0. Then now, looking at this one here, the sine x here is attached with x, then our x is the increment of x, then minus f of x, and our f of x is sine x, divided by the increment of f from the formula. Then now, when you expand this one from the double angle formula, you are going to have this guy, then minus this one here. Then now, our next step here, look at it, we put it in a bracket. Our next step here, we just carry this sine x here. This sine, the increment of x cos x to this place. Look at it here. Then after carrying it, then we use this one and this one divided by the increment of x. This one and this one here, this one here that we carry it divided by the increment of x. Then the next step here, we factor out sine x because it's common here. When you factor out sine x, remember cos x, the increment of x. When you factor out sine x, remember minus 1 here. Then now plus this one here, sine x cos x divided by the increment of x. Then look at it, what we did here. We take the increment of x here, cos here, look at it here. Then the next thing here, we take the limit of the increment of x tend to 0. Here is going to be 0 completely. That is how we get this 0 here. Then plus, then what we did here, as we take cos here multiplying this, and then we allow sine x, the increment of x divided by this, then we have this. And look at our limits here. Then completely here, according to the double angle formula, sine theta divided by theta, remember we say we have 1. Look at it, 1 here. Look at it here, is 1 here. Remember, it's 1 here. Then 1 multiplied by cos x here is going to be sine 0, because completely here is 0. 0 multiplied by this will say 0. 1 times this will get back to this. Then the next one, we say that is example. But another example show that cos x equal to minus x. Then what we are saying again, you are going to differentiate cos x with respect to x. The previous one is sine x. Let f of x equal to cos x. Then now, by first principle or tangent line, anyone, first principle or tangent line, this is tangent, as how it's stated from the formula from previously. Then now, anywhere you see x, you put x plus the increment of x as it stated. Then now, look at cos is attached with x and is equivalent to x plus the increment of x minus f of x, and our f of x here is cos x. We replace it here. Then now, when you expand this one using double angle formula, you are going to have this guy here, then minus this guy here. Then now, what we did next, look at it. What we did next, if you look at it here, what is here? This is cos x. When you expanded this one completely here, you are going to have this guy here. Then now, if you look at it, we bring this one here. We bring this one here. Then now, cos is going to be common. Then when you factor out one cos, you are going to have cos here remaining, and there is cos here is going to be 1, cos x. Then now, here, look at it, is sine x and sine x again after the double angle expansion. Then what we are saying here, look at it, after the double angle formula we have this, but we carry this one here, this minus sine x, sine the increment of x here. Then we divide this one and this one by the increment of x. We divide this one here by the increment of x. Then when we have cos x, cos the increment of x, and minus sin x, when we collect it, we discover cos x is common. We factor it out. Then when you factor it out here, you're going to have cos the increment of x remaining. When you factor it out here, that we collected, you are going to have 1 here. Then minus, because here is minus. Then the next thing here, we factor, we remove this sin x. Then we are left with sin the increment of x here divided by this one here. Then now, completely, when you put the limit of the increment of x tend to 0 of this guy here, you are going to be left with here and here is going to be 0 here. Then now, here is going to be 1 according to the double angle formula as how we explained previously. Here is going to be 1. Then here is going to be minus sin x multiplied by 1. Here is 0. And this multiplied by 0 is 0. And we are going to be left with minus sin x multiplied by 1. 1 multiplied by sin x, we get back to this. That is what we are saying. It means that when you differentiate any sin x, when you differentiate any cos x, you get back to minus sin x as according to the explanation here. Then now, this is the standard derivative. This is the function. This is the standard derivative. This is the function here. This is the derivative. When you differentiate sin x, as how we say, we get back to cos x, we prove it. When you differentiate cos x, you get back to sin x. When you differentiate tan x, you get back to sec square x. That one, if you want to prove that, maybe this one you can use some quotient too, because tan x is sin x all over cos x. When you let sine to be u, when you let cos to be v, you take it to the formula, you differentiate it, you're going to get back to this. When you differentiate cos, you get back to, when you differentiate sec x, you get back to sec tan x tan x. When you differentiate cot x, you get back to minus cosec square x. You can prove that using the other one. And look at the exercises we have. You can try it and submit it in our next class. Then the next thing is derivative, which is the last concept of differentiation, the derivative of hyperbolic function. The application of exponential functions and its inverse function are frequently being used in applied mathematics that gave rise to this section, hyperbolic function, that gave back we said the application of exponential function and its inverse function, which are frequently being used in applied mathematics, gave rise to this section. Hyperbolic function can be subdivided into hyperbolic sine and cosine, etc. Then example, find the derivative of the following hyperbolic function with respect to their various variable. Look at this one with respect to the various variable. Then you look at, before taking the derivative of the above function, let's remind ourselves of the definition of this function. Then when you have sine x is equivalent, the value is the same thing as this. Take note, sine x, the value is this. The inverse is sine inverse of x. Cos x, the value is this. If you look at the only difference here is negative, here is positive. Then you are going to have cos inverse of this, the same application. Then when we are differentiating the example given, let us be mindful with the values. Then now, sin x. Find the y dx. If y equal to this, find the y dx of cos x. To justify this result, we call that from the previous one, we say sine is the same thing as this. And let our y to be this. Let our y to be this. If our y is this, because when you multiply this one with this, we get back. Let our y to be this, then y prime is going to be, when you differentiate your y, this one here, you are going to have this guy here, because this one is multiplying this one, you have plus, because when you differentiate this one here, you are going to get exponential, but this one we are going to have plus here. When you differentiate it correctly, you follow the idea. Hence, when you differentiate sine, when you differentiate sine x, you go back to cos x. If you look at it, because what we are saying here, when you this is sine, and remember what is sine from the previous one. Sine is the same thing. The value is here. Then we let this one to be our u. Then when you differentiate this one with respect to u, here with respect to u, which is this, with respect to u. Sorry, when you differentiate this one with respect to x here to get to what your dy dx here, you are going to have this guy here. And if you look at this guy here, what we are saying, this guy here is cos from the value. Then you replace it as cos. Meaning, if you differentiate sine, you get back to this. Then let us go to this. The same approach here as how we solve this one here. You know that our cos is this. But if you look at this one is theta. We are using theta here. The other one we use what? We use exponential. Then the only changes where you see where you see here we use x, where you see this one you replace it, where you see x you replace it with theta here. There is no problem. Then now when you differentiate this one here, back here, you get back to sine. To justify this result here, we know our cos x is the same thing as e raised to power x from the previous one minus e raised to power minus x. But since from this example we are using a theta, you are going to replace this with theta. Then now, when you differentiate this one here completely, if you differentiate this one here, you are going to have this. And if you look at this one, is sine from the value. Then look at find the derivative of the function. This is the inverse now. Remember we said the inverse from the value here. The inverse is the order is this. Then the inverse, the sine inverse of theta, the sine inverse of this one sine. This is sine inverse of theta. Sine inverse of theta here cos. Then to justify this result here, we say that this is our y, and let our theta to be sine y. Let our theta to be, if our theta is sine y, you differentiate this one with respect to theta, you are going to have this. Remember from the previous one when we are doing logarithms, when you have this, you differentiate this one with respect to theta. Here you have this. Then when you this is the theta dy, you get this one. The theta dy, you get cos y. And when you are going to get dy d theta, you are going to have 1 all over what you get in the theta dy, which is 1 all over cos y. And what is y? Our y is defined as sine. What is y? Our y is defined as what? Our y is defined as something there. Now we define y is equal to this, then you replace it here. Now we determine y. We call that sine square y plus cos square y is equivalent to 1. Then cos square y plus cos square, sorry. What we are saying here, what is your y? Our y, remember, is cos. Then now, we say now to eliminate y, we recall that sine square y plus cos square y is equal, then cos square y equal to 1 plus sine square y. Then we eliminated that one. Then now, the second example, the student can try the second example, but the third example, which is this one, we are going to try it. Then what we are saying now, look at it, then cos square y equal to this. Then if you take the square of both sides, square root of both sides. If you take the square root of both sides from here, because if you take the square root of both sides here, we are going to have this. But remember, look at it here. If you take the square root of both sides here, then we are going to have this here, the square the square root. 2 here is going with the square root. We are going to have the square of here. Then 1 all over from here, 1 all over cos y here is equal to 1 all over cos y here is equal to, because we are looking for cos y, and we have gotten our cos y as the root of 1 plus sine square y. Then when we replace it here, in this place, 1 all over cos y, and our cos y, remember, is this. Then you just replace it as 1 all over cos y equal to 1, which is this. Cos y, remember, is we have gotten it as this. Then coming down here, the y, the theta is 1 all over 1 minus, what is our theta? Already our theta is defined, some here, y here. Look at it, equal to this. That's all. But remember, I want you to note that here is minus. Sorry, I did not corrected it, because since we are looking for cos y, we carry this one to this place here. We are going to have, remember, this is sine square y plus cos square y equal to 1. Then when you carry sine here to this place, you are going to have 1 minus cos square y. Then when you take the square root, you are going to have 1 minus here. There is minus here. Then coming down to this place to replace cos y, you are going to have 1 all over cos y, 1 all over cos y, and y here is this. Sorry, cos y here is this. Then there is minus here. Here is going to be minus. When you correct it, it's minus here. Then our dy the theta is 1 all over. Look at it here. Remember already our sine, we let it to be what? To be theta. Sine y is the same thing as theta. Sine y is the same thing as theta. Then coming down here, we replace this sine square. Because of the square, we have square. Then theta here. Then the same example, you can solve the previous, the number 1 and number 2 using the other one. Then look at the exercises that you can do comparing to other one. Then look at the first one. We say compute. You find the y, the t, using the limits of limit definition of the following function. You differentiate this one at t equal to 1, at t equal to 2. Look at this one. You know the respective one you are going to use. This one you can use direct, you can use first principle, you can use tangent line, you can use any one. This one you use quotient tool, the other one you use the other one. You know the types of derivative, you know the derivative, you know which one are you going to handle using all the respective concept of derivative. Thank you. Thank you very much for listening. You can do the exercises where you have questions that need to be asked. You can meet us, we put you through, and some step that is missing, you can, any step that is missing that you think you want to know the steps very well, maybe you did not understand correctly, you can still ask your question in the next class, or you can still meet us to ask that question by God's grace. We thank God. Thank you very much. We meet in our next class next week.